All right, welcome everybody. So I've been getting some good questions about the homework assignment. You've got until 4 o'clock on Thursday to submit that one. And I suppose that probably most people are going to use Excel for at least part of those homework problems. And so please upload both your hand calculations as a PDF file and then also the Excel file to Blackboard before 4 o'clock. And if you have any questions as you're working on the assignment, you can stop by my office, you can send me an email, or call me on Teams, and I'll be happy to help you out. Now today, if you look at the schedule, it says that the topic of our class is to introduce the first project. And so the first project is a system optimization project having to do with pumped storage, which I'm sure some of you are already familiar with and other people maybe hadn't heard about it before. So we'll talk a little bit about pumped storage. I'll hand out the assignment description and we'll have plenty of time for questions on that. And then just very briefly, I want to show you an add-in to Microsoft Excel that's going to be useful for the project. Okay, so do you have any questions before we start talking about pumped storage? Okay. So here's a visual representation of what we're dealing with for the project. What you can see in this photo is, I think this is the ocean and then an elevated reservoir. And this isn't a unique thing. There are a lot of different places where there will be a river of some sort and an elevated pond. And in a lot of cases, the purpose for having one body of water at a higher elevation, which is discharging to a lower body of water at a lower elevation, is simply that you're able to harness the power of that water moving downward, going through a turbine, spinning and generating electricity. And in one of our recent classes, I mentioned the word arbitrage. Does anybody remember that word and what the context was? What is arbitrage?
Pretty crude, buy low, sell high.
Yeah, it's when you're exploiting a discrepancy in the marketplace and you're buying something at a low price and selling it at a high price. And in fact, I mean, that's what every business does. And so not every business is arbitrage necessarily. Arbitrage, I think, is often used to describe where there's basically no transformation that's being added to the product. So it's not like, we're not talking about someone, a textile manufacturer buying raw cotton and turning it into a shirt. That's not necessarily arbitrage. One context that I recently heard of the word arbitrage being used was, does everybody know Sam Bankman-Fried, the guy who was arrested because he was operating that cryptocurrency exchange FTX out of the Bahamas? Well, he got his start in cryptocurrency because of what they were calling the Korean premium on Bitcoin. And for whatever reason, I think probably because there was more interest in Bitcoin in Korea for some period of time, the prices for Bitcoin on Korean exchanges was higher than other exchanges. And so he made many millions of dollars simply by buying Bitcoin on non-Korean exchanges and selling it on Korean exchanges. And he was looking for really small discrepancies in prices. You know, like if the price of Bitcoin on a Korean exchange was $10,000 and the price of Bitcoin on a non-Korean exchange was $9,990, you know, $10 doesn't seem like a really big profit. It's less than 1%. But you make up for it on volume and repeating that trade over and over and over. And so arbitrage is the idea that you can capitalize on discrepancy in prices in the market and pocket the difference. And so what we're talking about with pumped storage, I guess in a sense, is arbitrage because you're buying something at one time of the day and you're selling it at a different time of day. And the thing that you're selling is the exact same product as what you bought. You bought electricity and you're selling electricity. And the interesting thing in the case of pump storage is you're actually selling less electricity than you initially purchased. But the reason why it's profitable is the time of day that you're selling the electricity, there's more of a demand. So in the case of pump storage, what they do is they buy electricity at night and then they sell it during the day. And so can you think of reasons why there would be an oversupply of electricity at night and a shortage of electricity during the day? People are asleep at night, so there's not as much human consumption of electricity. You're not running your blender, you're not running your drill.
A lot of times, not all, like power plants will run throughout the night, like, for example, Marathon down there, it'll run through the night, but some, manufacturing plants might shut down during they might have like 9 to 5 business hours, so.
Very good. Yeah, it's not just individual consumer use patterns, but it's also industrial patterns are sometimes shuttered at night. And then, of course, a really huge component of electricity demand in the summer is cooling. And so cooling is less needed during the night. And so people are running their air conditioners during the day, and so there's this peak of demand during the day. And one of the ways that you manage excessive demand is by having differences in price. Now some places they do this, some places they don't. For instance, the electricity that I buy at my house here in West Virginia, I pay the same price per kilowatt hour all throughout the day. It's not cheaper for my electricity at night than it is in the day. Some residential customers do have variable prices, and a lot of industrial customers have different prices at daytime hours versus nighttime hours. My son right now is living in Paraguay, and he said that down there the electricity is cheaper at night than it is during the day, which is kind of interesting. So now, what this pump storage system allows you to do is it allows you to use electricity at night when it's cheap, and what they'll do is at night they'll pump the water from down low and they'll pump it up to the elevated reservoir. And they'll do that at night with, like, nuclear power, for example, is really hard to turn it down instantaneously when there's less demand at night. Even things like coal-fired power plants aren't that responsive where you can every hour turn it up and turn it down really nimbly, because in the case of a coal-fired power plant, what they're doing is they're building a big fire, and a lot of times they're generating steam, and so even if they can shovel more coal during the day and turn up the amount of steam production during the day, those fires don't immediately go down at night. So power plants have all this excess electricity production capacity at night and very reduced demand. And so if you're consuming the electricity to pump the water up here, now during the day you've got all this water up high and it acts as a battery. Potential energy could be electrical potential, it could be chemical potential, or potential energy can simply be the physical potential of some mass lifted up high, and then as it goes down through the turbine and causes the turbine to spin, then it can generate electricity. So the same pump system that was used to elevate the water at night, you can turn around the flow through the penstocks, and then during the daytime hours when there's more demand because people are doing industry, they're running their appliances at home, they're cooling their homes with air conditioning, when there's more demand, then these pump storage systems can sell the electricity at the higher rate. So here's just an illustration of our project. And this is an optimization project because I give you some hypothetical price data. Now, I don't think that most of you here are civil engineers. I know some of you are, but some of you are like electrical, right? And then what was your background?
Product and industrial.
Industrial, Jace?
Physics engineer.
Physics?
Industrial.
Industrial. So there are, were you civil? Yeah. Civil, okay. So we've got 4 civils and 4 non-civils in the class, and so it's evenly split. But I don't feel guilty giving you a civil engineering oriented project because you can never predict what kind of a project you're going to end up working on. You could be a mechanical engineer who ends up doing thermal systems. You could be a civil engineer who ends up doing mechanical design. You know, things get awfully scrambled when a company gets a project and then they're just trying to fill people onto the jobs. But you know, aside from that, the hydraulic aspect of this project is pretty straightforward. I've simplified some formulas for you to where I don't think anyone will be at a disadvantage if they haven't taken a hydraulics class before. So let's just go ahead with it. We've got an elevated reservoir, water flowing through a pipe, and this symbol is representing both the pump and also the turbine. So this is the machine which during the daytime, water is flowing downhill, it's spinning the turbine, and it's generating electricity. And then at night, the same machine, we say, we're going to put the electricity into it, and it consumes power to lift the water from the low reservoir to the high reservoir. So part of the reason why you have to use a pump is to lift the water, the elevation difference. But there's one more reason why you need the pump, and that's to overcome the friction. As the water flows through this pipe, then some of the energy is lost because of pipe friction. And so this turbine is going to be not producing as much electricity as it otherwise could have if it wasn't for the energy that's lost due to friction through the pipe. So one of the things that you're going to be looking at on this project is how big should this pipe be? Because the bigger the pipe, less energy is lost due to friction, but then on the other hand, it's also more expensive. So your objective is to maximize profits. Ultimately, that's what I'm going to be asking you to calculate is for a certain pipe size, what's the best flow rate to operate at? So you're going to be optimizing that parameter. Then also, among the pipe sizes that are available, what can generate the most money? So we've got a reservoir, water's flowing through a pipe, which causes resistance to flow. This is a pump at night lifting the water uphill. During the day, that's our turbine and power plant, which is generating electricity, and the water is flowing down to that lower reservoir. So you can calculate the flow of water. The flow rate is Q. Q is the flow rate. V is the velocity of the water through the pipe. And I give you in the handout all the formulas that you need. So don't get too intimidated or flustered quite yet on any of these hydraulic calculations. But it's just the basic, you know, every industrial project, whether it's elevators or a pump storage system or anything else, is going to have boundary conditions, and then it's going to have efficiency factors, and it's going to have constraints. And so this project is no different. The amount of power that you can generate kind of dictates how profitable your project is going to be. Because if you can generate a lot of power, then you can sell it and you can make more money. Not every system is 100% efficient. And so what this formula is saying is that your system is 75% efficient at converting the hypothetical power into power that can be sold. And so H is the amount of head that's available, which I'll explain in a moment. Gamma here is the unit weight of water, and Q is the flow rate of the water that's going through the pipe. So P is how much power you can sell. And like right now, I think my rate that I pay for electricity is around 12 cents a kilowatt hour. And in this project, what I suggest is that the company that operates this system has to pay 1 cent per kilowatt hour during the night to purchase the electricity to pump the water uphill, and then they can sell the electricity for 12 cents per kilowatt hour. And so their arbitrage opportunity is the fact that they're buying something for 1 cent and selling it for 12 cents. And it seems like a license to mint money, but all of these materials aren't free. You have to pay to build the The upstream reservoir you have to pay to lay the pipe. The power plant costs money. So this H that's in this formula, which basically what you're selling is power. So we care really a lot about each of these terms because the bigger H is, the more power you can sell. And if Q is high, you can sell more power. So the more the water is flowing through the pipe, then that maximizes the amount of power that you can sell. But there's a problem. This term H, which is the head that's available, you can think of it as the energy that's in the water. It's affected by friction through the pipe, which I already mentioned that when the water goes through the pipe, some of the energy is lost because there's a resistance to fluid movement through the pipe. And the resistance to the fluid movement is dependent on the velocity of the pipe and the diameter of the pipe. So this empirical formula here just tells you how much head is available when you're generating power. And you also are going to have to buy the electricity to get the water up to the elevated reservoir. And so you're going to be consuming some electricity. Now it's only 1 cent per kilowatt hour, so it's certainly not a huge cost compared to the value of what you're selling when you generate power. But again, it's not 100% efficient. So you're going to have to buy more power than you're able to sell. And I already mentioned that right at the outset that, maybe you'll be buying 2,000 units of electricity, but only able to sell back 1,000 units of electricity. And the reason why is that the power plant isn't 100% efficient, the pump isn't 100% efficient, and you're losing energy as the water flows through the pipe, and you're losing energy both ways. You're losing energy as the water's flowing downhill, but also you're having to add even more energy to the system to overcome friction when the water is going into the reservoir uphill. So this H is how much head is required when you're pumping. And again, the faster the velocity through the pipe, then the more energy is required. So initially I was saying, like, you'd want to maximize Q to be able to sell a lot of this power. You have to have a lot of water flowing through the pipe. But if you have too much water flowing through the pipe, then there's going to be really a lot of resistance, and you're going to find a point of diminishing returns. You've probably heard that phrase before, the point of diminishing returns, which means there's going to be a certain point where if you make the pipe bigger and bigger, your revenue's going up, but then if you continue, the revenue starts going down because the cost of the pipe is higher. And the same thing is true for this, I guess we could say, is profit. And this is flow rate. What you're going to find is there's some perfect flow rate for a given pipe diameter. Let's say maybe this pipe is a diameter of 0.75 meters. This curve would be specifically for the 0.75 meters pipe. There's going to be a sweet spot where you maximize your profit, and I want you to find that sweet spot. I want you to be able to go through the calculations and find out, optimize the system to find out where is that maximum profit point. And so these equations are the governing equations that dictate, for example, how much energy you're going to be consuming to get the water up to the reservoir, how much energy you can sell based on the friction that's reducing your head. And here are some pipe costs. So you're selling the electricity from 8 p.m. You're selling the electricity from 8 a.m. until 6 p.m. So that's 10 hours a day, right? So you're selling electricity 10 hours a day, and you're buying electricity from 6 p.m. to 8 a.m. So that's 14 hours a day that you're buying the electricity. And what we assume is that there's going to be a balance between how much water you pump uphill at night and then the amount of water that you can consume during the day is the same volume. Like, if we go back to a picture of one of these, if this pool becomes empty during the day, then you're out of water. You can't generate any more electricity. So all of the water that you want to be able to pump downhill during the day, you have to have pumped it uphill at night to make sure that it's there. The flow into the reservoir and the flow out of the reservoir are in equilibrium in a 24-hour cycle. There's also the time value of money aspect that we have to think about in this project. Because we know how much it costs to buy the pipe, and we know how much it costs to buy the electricity, and we're going to have to pay to make the reservoir. It says here that it's $200 per 10 cubic meters. So you're going to calculate like the volume of the reservoir that's needed to have enough water up at the top. And we can determine how much electricity we want to generate, and so we're going to have a pump that's a certain size, $60,000 per cubic meter per second of pumping capacity. We're going to have to pay for the power plant. So all of these things are fixed costs in the they're costs in the present. So you're going to be paying a lot of money now to initiate this investment. So cost of the system at time 0. And then you're going to be getting some profits over time. And it's through 50 years. And our interest rate that applies in this project is 7%. So then that's another factor that dictates how big should this system be. Because you're going to be spending really valuable dollars today to buy all this equipment, and you're going to be recouping the initial construction cost with revenues in the future, which become smaller and smaller in the future because they're so distant into the future. If we discount them back to the present, then their contribution towards the present value becomes pretty minor. Okay, I'll pause for a moment and see what questions you've got so far. Ben, you look amused.
Well, I've got a question, but I think I might be a little bit in the weeds here.
Go ahead.
So, when you're pumping,
Yeah.
you will be able to control the rate at which you're pumping.
What we're going to assume is that you pump at the same rate during the entire 14 hours that you're pumping, and then the generating flow rate is constant through the 10 hours. So
Okay.
those are two different flow rates, by the way, because you're going to be pumping for 14 hours and generating for 10 hours. So,
Because I was sitting here thinking, I was like, well, as your head changes, your velocity down the pipe can change, and
Mhm.
there's going to be a sluice gate to control the flow.
right.
I think I was getting a little in the weeds.
Yeah, so let's just assume that this is a really shallow but wide reservoir up at the top so that the elevation of the water surface doesn't affect our head. So we don't have to worry. The head is only influenced by the rate that we're pumping and the head loss due to pipe friction.
Okay. That clears up my...
It's a good question. Are there other questions? Sometimes at the beginning of a project, it's so overwhelming and confusing you don't even know what questions to ask. So
Is the
hopefully,
unit water 9810?
pardon me?
Is the unit
Yes.
water 9810?
Yeah, yeah, so gamma, it's in the handout, I believe, but it's
Okay.
9810 newtons per meter cubed. Yeah. So this formula here for the gamma, if you're trying to find out the number of kilowatts of power that can be generated, you'd multiply it by the head by 9.81 kilonewtons per cubic meter, and then the flow rate in terms of cubic meters per second. Let me give you that handout right now so you've got it, and I'll give you some time to look it over. I'll pause from talking, and we'll see if there's more questions.
Let's get started.
Yeah, let me tell you about this getting started thing, because I mentioned I've given this project before to students, and the first couple of times I gave the project, that third page wasn't in there. But I got the same questions so many times, I thought, how can I give them some hints that will overcome these same questions and hang-ups that I'm getting every single time? And so I thought, we have to reason through kind of like the step-by-step problem-solving process that can make this seem more real to you and less abstract. Because the problem a lot of students were doing is they were going straight to Excel without really understanding what was happening first. And so here in the getting started, what I'm suggesting you do is do some hand calculations. Because if you can have a set of numbers that you're confident in, that you've done by hand, when you start setting this up in Excel, you can put in the numbers that you already know and look for the answers that you know are right. And if you have hand calculations that Excel is able to calculate, and then you can start tweaking the dials on the optimization, then it'll save you so much time and you're much less likely to avoid mistakes. So this getting started section is basically, in particular, I think it'll be useful to the people who don't have any background in hydraulics. And so let's just look at this first part here, generating power, for example. So all of the formulas that you need are here, and some of them are embedded along the way. But let's just say that Qgen, so this is during the day, that's the flow of water that's going downhill. So if you have 1 cubic meter per second of water, and it's going through a 1 meter diameter pipe. So what this series of questions is asking you to think about is, okay, how many hours per day are you generating power? Well, earlier in the description, it says that you're generating power from 8 a.m. until 6 p.m. So that's 10 hours per day. So if you know the 10 hours per day, I say, well, how many seconds is that? Okay, so if it's a certain number of seconds, and you know the Qgen is 1 cubic meters per second, now that is going to tell you how big the reservoir needs to be. The reservoir only needs to be as big as the amount of water that you're going to be pumping from it during the day. Like if you're only going to be using 5,000 cubic meters during the day, there's no reason to make the reservoir 10,000 cubic meters, because that's just wasted money. It would be excessively costly to do that. So this is basically like saying, okay, if this is the flow rate, and when you set it up in Excel, all of these calculations are going to be dependent on cells that you could change in Excel. You know, rather than typing the numbers themselves into Excel, you know how sometimes we click on a cell location, and then what you can do is you can change the number in that cell location and see all of the calculations automatically adjust. So we're going to be using that advantage to automate the calculations later, but by going through these step-by-steps on paper, then you can verify your spreadsheet set up correctly. So you know how many seconds it is, because it's, you know, how many seconds are there in 10 hours, basically. And then for 1 cubic meters per second, then what's the volume that's needed? Okay, so we've defined the volume, therefore you could calculate the cost of the reservoir, because it says here the reservoir is $200 per 10 cubic meters. Okay, so you've already figured out for a certain flow rate the reservoir cost that's needed. All right, now part C, for a certain generating flow rate of 1 cubic meter per second, what's the water velocity? Now this is for a 1 meter diameter pipe, and I give you the formula for a circular pipe. The cross-sectional area is pi d squared divided by 4. So the area is pi 1 meter squared divided by 4. So that's 0.78 square meters, I think. 0.7, so it's a certain cross-sectional area, so then the flow rate divided by the area, the velocity is 1 cubic meter per second divided by 0.78 square meters. Maybe I ought to check that since I'm writing it on the board. 7854. Okay, so then 1 cubic meter per second divided by that means the water velocity is 1.273 meters per second. Okay, so we found out what's the speed of the water going through the pipe. Now remember, all of this is based on if the flow rate is 1 cubic meter and if we're using the 1 meter diameter pipe. Once you get it set up in your spreadsheet, you can make all sorts of changes. Like you could change the pipe diameter, and then you could see how all of the calculations are different based on a different pipe diameter. Or you could play around with the flow rate and find out how does the velocity change based on different flow rates. So once you've got the generation velocity, then you can calculate how much head is available. Hgen is the formula that you're using. So here is the Hgen formula. So how much head is available is 100 minus whatever the velocity is to the 1.85 power divided by the diameter to the 1.17 power. So you can do all these calculations by hand. And here at the bottom, the cost of the power plant should be $590,760. And if you want to check on the answer to every one of these steps along the way, you can stop by my office or send me an email or give me a call, and I'll tell you if you've got the right number. I don't want to tell you what it is because I really want everyone to individually on their own go through the calculations, because the best way to be able to set this up on the spreadsheet is to start off with a good set of hand calculations to begin with. All right, so that's what the getting started is all about. I think that if you go through these calculations, then that's going to help you to design what the spreadsheet should look like. And in fact, your spreadsheet could be like on one row, you calculate this thing. On the next row of the spreadsheet, you calculate that thing. The row below it, you calculate the next one. And you may come up with some formatting, have some things in bold or whatever, but all of these dependencies will allow you to optimize and iterate in the end. All right, so are there other questions as you've been looking through it so far besides, that was a good question, what is this getting started? Are there other things that aren't clear that I need to explain? All right. Well, let me just kind of give you a hint of where this is all headed and show you a tool in Excel called Solver. Now, Solver isn't turned on by default, so the first thing I'm going to do is show you how to get access to the Solver, because if you open up Excel and go to the Data tab, you may not see Solver over here on the far right, because by default I think that the Solver is turned off. And so it's here in the options, I think, add-ins. Yeah, so see this Solver add-in. If you go to the Solver add-in, you got to, probably for most of you, the Solver add-in won't be turned on by default. And unfortunately, the one thing about turning it on is it makes Excel about 4 times slower to start. I don't know why this one add-in makes it so much slower to load Excel. Without the Solver add-in, it's less than 1 second, but then if you turn on the Solver add-in, now Excel takes a lot longer to run. So if you go to the Data tab over here under on the right side, right now you can see that the Solver add-in isn't available. So the way that you turn it on is if you go to File and then Options, and then on the left-hand side of the screen at the bottom is Add-ins, and then Manage Excel Add-ins. So click on Go, and then we're just going to click Solver Add-in. OK. By the way, I've got a video on YouTube where the only thing I do is show how to turn on the solver add-in, and that's my #1 video on YouTube. I've got more views. It's like a minute long, just showing how to turn on the solver add-in. Yeah, that's my contribution to mankind, is showing people how to turn on the solver add-in. So now you've seen it too. And look, here it is. It's under the Data tab. Okay, so this solver add-in is what's going to allow you to optimize, because if you turn it on and click on it, it does something a little bit different than GoalSeek. Remember, I think if you've used GoalSeek before, it can be useful if you know what the target amount is. But if you're just trying to find a maximum or a minimum, Solver is what can do that for you. And in our case, we're trying to maximize profits, right? We're trying to find out where's that best operating point. And I drew it on the curve before, on the whiteboard before, as something looking like this. So for flow rate increasing, what we want to do is have the maximum amount of money. So the more flow rate you've got, you can sell more electricity, but then you're going to get to a certain point where, because the head losses get more and more extreme, if you have higher and higher flow rates, you're actually going to be losing energy through the pipe. So there's this perfect operating point, and we don't know yet how much it is, and so we wouldn't be able to use just what if analysis GoalSeek, because we wouldn't be able to find out what flow rate gives us the maximum profit, because with GoalSeek you have to know what profit you're looking for. And so we don't know, like, is it $10,000? Is $10,000 the profit that we're looking for? Or is it $12,000? We don't know. So it couldn't find what's the best flow rate operating point. But Solver can, because Solver has the ability to search for a maximum. And you're going to be looking for what is the flow rate that gives you maximum profit. So just to play with Solver really quickly, let's try the following function. Let me erase the whiteboard here. Just to illustrate what it can do. If our function was y equals x squared minus 3x minus 2, and we want to, I think this one we're looking for a minimum y. So minimize minimize for this one. Yeah, so we've got this function. I'll just type it in here so that it's on the screen as well. Y equals x squared minus 3x minus 2. Okay, so in this column I could put x, and in this column I could have y. And just to play with some possible values, let me put x from -4 down through 4, and then I'm going to find out what's the resulting y by using that function and this value of x for each of those different values. Okay, so equals x squared minus 3 times x minus 2. Okay, 26. So let me drag this down. We want to find out what's the minimized, what's the lowest value. So if we go further beyond 4, it's going to, I think, continue to increase further. So just based on what we see so far, it looks like the lowest value is -4. But that's actually not the case. There is a value of x which gives you an even lower value of y. Now you could solve this directly. You know, you just solve, well, no, I guess you'd need to know what it is. So let's try the solver function here. So solver, our objective is, now we could use, by the way, we could use any one of these rows. So let me just do it on the bottom row. I'm going to apply the solver function to the very bottom row. Okay, so what I want is I want this cell to be minimized. So I want the lowest possible y, and I'm going to allow it to change the x value that's going in. Now all the rest of these options you don't have to play around with. The different solving method is about like how does it jump around in values. You know, does it go downward through negative values and then upward through positive values, or you know, how quick are the increments that it sets. In the options you could set the convergence criteria for like how much precision there needs to be. And so if you're getting an answer that isn't quite accurate enough, you can add additional zeros here to the precision. And sometimes I've had to do that on certain problems where it was just, it was saying, it was quitting, and it wasn't yet actually solving for the value that I needed. So I just had to put in some more zeros here to improve the precision. But for our project, I don't think we'll have to change any of these options. What we're just doing is we're saying we want this last y value to be minimized, and we're going to give it permission to change what's in A15. So when you click solve, it played around with it, and it found that 1.5 is the x value that gives us the lowest y value. So the lowest y value is negative 4.25. And if you click OK, then it will keep the solution that it found. So I'll just click OK. So that shows optimization. We didn't know what target we were looking for. We didn't know what was the lowest possible y value, but Solver allowed us to find it. So as it applies to the project, the thing that you're trying to identify, if you look at part A, is just for the 1 meter diameter pipe.
So we will maximize profits by changing the velocity of the 1 meter pipe.
Changing the flow rate.
Yeah.
Velocity affects flow rate, but like the master variable is what flow rate should you operate at for each of these pipe diameters. You've got a 0.125 meter diameter pipe, a quarter of a meter, half a meter. So yeah, the master variable is flow rate. And in fact, there's only one master variable, because if we go back to this getting started, there is both a Q gen and a Q pump, but the two are related. When you go through this getting started, you're going to see how the Q pump is related to the Q gen. So there's really only one variable. So you're going to basically, the in, like this was, I'm saying X and Y, what it's going to be is flow rate and money.
Shouldn't the flow rate be equal though? Because you wouldn't want to pump more, like you just said, pump more water up. It's coming down. So.
But it's different number of hours per day.
Oh, okay.
Yeah. So it's 10 hours versus 14 hours. But you're right. You want the flow into the reservoir and the flow out of the reservoir to be the same. So if you've got 10 hours,
So your pumping flow will be slightly lower.
your pumping is,
It'll be slightly lower if you're doing it for longer.
it's 10/14 lower. Because
It's
10
5/7
hours,
lower?
well, yeah, 10 hours at Q gen is equal to 14 hours at Q pump. Because you're pumping uphill at night from 6 p.m. to 8 a.m. So that's 14 hours that you're pumping uphill. And you're pumping downhill. The generating flow rate is for 10 hours. So, you know, there's equilibrium. The volume, Q gen would have been down, equals the volume up. The two volumes are the same. But the flow rates are different. You get it. All right. So back to this idea of optimization, what we're trying to do is find out, like for example, for each diameter, for each of these diameters, what's the best flow rate and how much money can you make? So the best flow rate is, by definition, it is going to be maximizing the profit by changing the flow rate. And so it'll go and try a lot of different flow rates, and it's going to find the flow rate that gives you the most profit. So down at the very bottom of your spreadsheet, as implied by the getting started hints, if you know the cost of the power plant, the cost of the pump, the cost of the electricity, you add together all of the costs, and then you add together the revenue that you get. The difference between the two is your profit. Profit is revenue minus costs. And so if you look at the things that cost money, what costs money is the pipe itself, the reservoir, the power plant, the pumping plant, and that's that. But then the tricky thing is, this is happening for 50 years, right? So you're going to have to think about what is the amount of revenue that you get in year 1? What is the amount of revenue you get in year 2? You know, all of those revenues are the same, but they're recurring payments effectively, because you're going to be finding out.
Will the cost of the electricity also go up?
No, we're going to assume that that's constant. In reality, it would, but just to simplify things, we're going to say that throughout time, it's still the same 12 cents a kilowatt hour that you're selling it at and 1 cent a kilowatt hour that you're buying it at.
That was a question that I had.
Yeah.
That would have got tricky.
Yeah, maybe next semester I'll give them that at your suggestion, and I'll let them know that you're the one who suggested
You
it.
should also tell them that the head can vary, variable head.
Yeah.
So you can put a sluice gate in. to control the
Exactly.
flow.
Yeah.
I mean, you could make this very.
Oh, well, the biggest gift that I've given you maybe is that you're calculating the head. This is effectively the Hazen-Williams equation. So if I made you use Darcy-Weisbach equation, where the friction factor depends on the flow rate, things would get really hairy. But that's not what this is about. This is about the optimization. It's not about the hydraulics, as much as I wish it was about the hydraulics. It's about the optimization. So it's about using Excel to find that operating point, and then discounting the future revenues, because we've got all this money in the future. So you're going to have to, at the very end, do a I guess it would be equals PV function, where you've got the number of periods, because you're going to find out per year what is the revenue per year, and then what is the net present value of that revenue. Because basically you'll find out, you know, like for a certain operating point, what its initial cost was, and then what is the net revenue each year, and then the present value of it at 7% interest rate for a number of periods, 50, and then that recurring revenue that you're getting will be a payment. So it will occur down in that third field, you know, because it's going to be every year you're getting the same amount of net revenue, and we want to know what's the present value equivalent of that. So I've got the answer. So if you want to go through the getting started and check on that with me, or if you want to, you know, go all the way through the whole project tonight and just, you know, not even sleep tonight, first thing tomorrow, send me an email with your answer to the whole project. I'll let you know that you got it right. However you want to do it. But you've got until the 23rd at 4 o'clock. Are there other questions about either solver or pump storage in general? Let me show you one more picture of pump storage. I think I can find it. I see it every time I'm in Colorado, because the place I like to go hike, it's actually Twin Lakes.
Do they ever use like pump storages also for water supply, or is it always for generating power?
I don't know what the application would be for water supply. I mean, well,
Well, you'd have like a gravity head like a water tower.
yeah, like would
I
they,
don't know why you would, if you're using it for water supply, why you would send it down for electric, send it back up. I don't know, it was just kind of.
yeah, I mean, they definitely, like, the water, you know, the water that I drink doesn't come straight from a pump at the Ohio River to my house. It goes to like a storage tank. And so they lift it to the storage tank and then they can switch off the pump. And so at night, there's that elevated tank that's provided pressure to the house and a pump doesn't have to constantly be running. So, I mean, there's economic value in having it in that elevated tank simply so that you're not having to run any equipment continually. But there's a more and more emphasis on pump storage. It used to be that nuclear and pump storage would go hand in hand. Like, you know, but then nuclear went downhill in the 80s. Fewer places were, you know, there hasn't been a new nuclear power plant built in the United States in probably 30 years. But recently, pump storage is getting a lot more attention because of wind power and solar. You know, everybody always says, well, what are you going to do on a day when it's not windy? Or what are you going to do at night when the sun isn't shining? Well, what you can do is you can store that power through pump storage, and then that provides a nice renewable means of storing power through the night. And a related technology is a gravity battery. And that gravity batteries is something that they're thinking about doing here in West Virginia, where what they'll do is basically they'll have a really heavy weight and they'll dangle it above a mine shaft. And think about if that weight is going down, it could like spin a generator, like as it's going down, spin a generator, and then at night when they've got leftover electricity from a nuclear power plant, or if this was like trying to store power from a solar, you'd use the power to lift the heavy weight back up again because it's consuming electricity to do that. And so gravity batteries are a similar thing to pump storage. And the advantage of the gravity batteries is then you're not having evaporation because you do lose some water, especially in an arid place like Colorado, which is where I see pump storage a lot. You know, it's very dry in Colorado, so they're losing a lot of this precious water. But
I did something similar for like my research project.
Okay.
It was a solar-based cryptocurrency miner.
mm-hmm.
The calculations on that were like terrible though, because like the amount of money you get for like mining Monero for like a year is not even worth it, but for the amount of like electricity I was consuming. So,
Yeah.
but,
Yeah, the only place cryptocurrency mining really works is like places like Iceland where they have effectively free geothermal power, or, you know, corrupt places where you can plug into a coal-fired plant and the local commissioner looks the other way, or, you know,
I lived in the school's electricity too, so it kind of gave me.
Yeah,
but
yeah.
It still wasn't.
There's that.
It still wasn't
Put
anything.
that tuition to work.
Exactly. All right. So let's wrap it up. I guess we'll finish a bit early. Just as a reminder, the homework assignment is due on Thursday. And then this is kind of lingering in the background. If we look at the schedule, here's the schedule. So you're going to do homework 3 on Thursday of this week. And then it's going to be homework 4 on Tuesday the 14th. So you'll have a little bit of extra time to do homework 4. Then we're going to have our midterm exam on Thursday the 16th, and then it's the following Thursday after that that the project is due. So you're getting this kind of early in the sense that there's going to be some other things on your plate between now and then. You're going to have to maybe multitask a little bit. Spend some time on the project, spend some time on homework 4, spend some time on the project, spend some time getting ready for the midterm, and so on. Okay, so when we get together on Thursday, please bring your computers because we're definitely going to use them for the in-class exercises that we do on Thursday. And that's it for tonight.